Hello, we are Team 3, and we'll be presenting on the analysis and redesign of a manual meat grinder. Meat grinders are used to process meat for various grinding and stuffing applications. A key feature of this tool are the exchangeable plates for varying meat cuts and sizes. This tool can also be used for fruits and vegetables. Our primary customer group is going to be adults in residential settings. This customer group is more interested in smaller batches of food and a more portable solution that doesn't require electricity for applications such as camping. Our secondary customer group are restaurants and butcher shops, and they're more interested in larger capacities of food and a more industrial and durable application. In terms of functional analysis, the task function here is to grind food, and the primary basic function is to store food and convert the texture. In terms of storing food, we want to contain the unprocessed food, especially for a larger capacity for our secondary customer group. And we also want to prevent spilling. And in terms of converting the texture, we want to transport and break down the food. And some other notes is that we want to facilitate cleaning, enhance portability, and then also prevent blockage within the system.
Here we have a CAD image of a meat grinder disassembled in a way that allows one to see where the parts should go in relationship to one another. These are the two feasible assembly sequences for the product. The auger, cross knife, and grate grinder have to be assembled in a specific order, which is seen in both sequences. The difference between these two is that in sequence 1, the clamp is assembled at the end, while in sequence 2, the clamp is assembled first. This table compares the two assembly sequences based on the criteria listed. Having only one major difference between the two sequences gives them very similar totals, with sequence 1 being the better of the two. Assembling the clamp first creates an inconvenience in handling during assembly, which is why sequence 2 receives a lower score in that category. Both sequences require you to hold and reorient the body when assembling different parts, which is why neither have perfect scores in ease of assembling in parallel and in ease of transferring and handling.
Here is our function component mapping matrix for the manual meat grinder. The matrix shows the relationship between the individual components and the basic functions that were at the end nodes of the FAST diagram. Most of the components served only between 1 to 2 functions with the exception of the auger. This indicates a large potential impact on the grinder if the auger was to be redesigned. The functions transport food and break down food are influenced by many components, which shows that these functions were important considerations when designing the grinder.
This is our bill of materials for the manual meat grinder. For this, we assume that the total production volume would be 200,000 units per year. We also assume that the tooling life would be the same as the production volume. The assembly labor cost is estimated to be $15 per hour. The total manufacturing cost per unit came to $48.10. This is approximately 70% of the retail price of similar manual meat grinders and their attachments.
Comparing the functions for each of the customer groups, the primary being household users and secondary being those who use it for commercial applications, we determined function difference occurs when containing unprocessed food and product enhancement, which is shown by the different components between our two designs. Each of these designs shares the platforms listed on the left. The modules or differences in these designs are the feeder tray and the S-curved arm. The first module is the feeder tray seen in the center of the screen. This tray is easily attached to the neck of the grinder, allowing the user to feed the grinder larger quantities of meat faster. The second module is the S-curved arm. The new shape of this arm allows for greater torque, making the meat easier to grind for the secondary customer group. Delayed product differentiation is essential to keeping the manufacturing process streamlined and efficient. In the first assembly sequence, you can see product differentiation occurs, but there is still a part added after the clamp that is common to both assemblies. By moving this common component to earlier in the series, we are able to streamline this process.
For design for manual assembly, we made 2 design modifications. The first modification is to the lock ring, which previously had a screw feature, and we added instead snap fits to the body so that this will in turn reduce time for insertion, which also aligns with DFA 11. And then the second design change we made was to the feeder tray, and we redesigned it to be round and symmetric. This will in turn reduce our handling time, which aligns with DFA 6. And you can see the photo on the bottom. So both these design changes helped reduce our total assembly time and then also efficiency. So our total assembly time reduced by 4.45 seconds and our efficiency improved by 2% by making these design changes.
For design for automated assembly, we made 2 modifications, both of which serve to increase the arm orienting efficiency and decrease its handling and insertion costs. The values highlighted in yellow in the first table. These original high-cost values are attributed to the unsymmetrical arm and the need to hold the arm in place in order to maintain its orientation. To improve the efficiency and reduce costs, we modified the body following DFA 11 and added an alignment feature. With this, the arm no longer has to be held in place when being secured. The arm itself is modified following DFA 6. The non-standard hole in the arm is made symmetrical, making orientation much more efficient. From the second table, which shows the cost of assembly for the modified design, we see that these modifications do increase arm orienting efficiency and reduce the arm total assembly cost by 51.1%.
After redesigning the feeder tray for manual assembly, the key geometry was the tray's bowl-like inner surface, which determines the amount of food that can be transported and broken down at one time. Note that transport food and breakdown food were component-dense functions in the function component mapping matrix. The key dimensions to represent these features are the tray's inner diameter and inner height. For these dimensions, we require a tolerance of plus or minus 1 millimeter, and the remaining properties are shown in the table. Based on the property table on the previous slide, the possible processes are sheet forming and machining. We selected sheet forming due to the part's smaller thickness and sheet forming's ability to pierce and shallow form the bowl section of the feeder tray. Welding would also be required as a secondary process to attach the upper bowl section to the lower cylindrical section of the tray. After redesigning the arm for automated assembly, the material of the part was changed to aluminum alloy as opposed to cast iron due to its lighter weight and its ability to withstand higher pressures. The key geometry we focused on was giving the securing notch a more symmetric orientation rather than being at an angle to increase part symmetry. The key dimensions to represent these features are the armhole's inner and outer diameters. For these dimensions, we require a tolerance of plus or minus 0.5 millimeters, and the remaining properties are shown in the table. Based on the property table on the previous slide, the only possible manufacturing process for the arm is die casting, which is also ideal for capturing the arm's curved shape.
The initial feeder tray design required multiple steps, bends, and piercings to create the shape using sheet metal forming. In the redesign shown on the right, we reduced the amount of individual bends and steps by having the metal pressed into a bowl shape. As seen in the table below, reducing these steps greatly reduces the cost per part from $2.11 to just 74 cents. The original design for the arm included details that required the arm to be created by traditional machining. In addition, the different sized holes and asymmetrical design added to manufacturing time and cost. By creating a simple symmetrical arm, the part is able to be formed by die casting. This reduces the cost per part by almost half.
For our design of a product service system, we decided to implement the free replacement of damaged meat grinder attachments and the inclusion of a tutorial book with the purchase of the product. When a customer's attachment is broken or damaged, the company will send a free replacement. The customer will then send the broken part back to the manufacturer using the same packaging that the new part came in. This will result in a pleasant customer experience with the manufacturer and a decrease in the impact on the environment since the same packaging is used. Once the manufacturer receives the damaged part, the part will be recycled and the material will be used towards making new parts. The tutorial book that is included in the purchase will give step-by-step instructions on how to properly use the meat grinder and its attachments. This will show the customer that the company wants to ensure the user has a positive experience and will develop a relationship between the user and the company. The tutorial book will also guarantee that the customer is using the meat grinder correctly and will increase the life of the product, resulting in a decrease in cost for the customer since they will not have to replace the product sooner than predicted. Overall, the redesign of the meat grinder resulted in reducing the assembly time by 4.5 seconds through the reduction in insertion time of the lock ring and reducing the handling time due to the addition of the feeder tray. There is also a reduction in assembly cost. Some pros of our redesign are the product can be easily disassembled for cleaning, only one fastener is required for each of the grinder, handle, and clamp, and the S-curve of the arm allows for the user to have more torque when grinding meat. Some cons are the force from the process of grinding meat can result in the snap-fit locking ring coming apart, and the addition of the feeder tray increased the number of parts from 10 to 11. If we had the opportunity to have a different approach to the product, we would have spent more time investigating an alternative to the base clamp of the meat grinder.